Hello and welcome back to differential equation, section 2.3, homogeneous equations with constant coefficients. We are now defining, we're going to talk about the way to solve differential equations of the higher order. We're going to utilize characteristic equation, which is going to resemble a polynomial. We find roots. Roots can be real, repeated real, or complex, which will trigger different types of solutions for our differential equation. So we start the whole thing by realizing our constant coefficients. So this is numbers in front of y prime, y double prime, and so on, not functions, right? Which I said constant coefficients. So the equation will be of the form an y to the nth derivative plus an minus 1 y n minus 1 plus an minus 2 y n minus 2 plus dot 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 dot, there we go, plus a2 y double prime plus a1 y prime plus a0 y equal to 0. Homogeneous case, which means equals to 0 on this side. Now, what happens here is that we assume solution e to the r x, and then when we plug all of this in, certain things cancel, but you see that actually what happens here is you get a characteristic equation which is the polynomial and resembles exactly the differential equation that you consider. So if you have now, for just to explain this in the simple terms without chasing all of these guys, we can take a look at the second order differential equation with constant coefficients. So you take ay double prime plus by prime plus cy equal to 0. And from there, you can derive the characteristic equation, which is ar squared plus br plus c equal to 0. Now, this one over here is called characteristic equation. Now, this derivation between the two worlds happens when you assume the solution of the differential equation to be e to the r x. Those of you who want to do this derivation and see how this equation becomes this characteristic equation, you can do that derivation quickly by assuming y equal e to the r x, differentiate twice, plug into this, you will see it cancels, all of these e's cancel, and you are left with the characteristic equation. So if you are interested in that kind of proof, it literally takes 2 lines. You will be deriving this characteristic equation from there. Now, if you are just looking at this real quick, observe that A is A, B is B, C is C, right? You have all of that going. You also have the second order gives you the second derivative gives you the second power. First derivative gives you the first power. And then I told you this the day one, 0th derivative, which is original function, gives you r to the 0, which is 1. So characteristic equation is going to look like this. If you have the third derivative there, you will start with a r cubed, and then b r squared, and so on. So that's how it works. Now, if you observe this thing over here, it's a polynomial, right? In respect to r. And r is in the exponent of your solution for the differential equation, because we got this by assuming the solution y equals constant c times e to the rx. So clearly, by just factoring this or using quadratic formula or whatever other witchcraft you know to solve this equation, you will get those r's. And as I said, those r's are either real, complex, or repeated reals. So we are going to solve one of these differential equations. This is going to be extremely simple, but that's how we start, right? And then say, then use r's to compile y equals c1 e to the r1t plus, I can't fit anything. To compile y equals c1 e to the r1t plus c2 e to the r2t. And then if you have, right, other things, we're going to discuss what the other cases are. So I just want to run through one example for all of this to make a little bit more sense. So say you have, relax, y double prime plus 6y prime plus 5y equals to 0. Now, you can immediately skip the step and go into r squared plus 6r plus 5 equals 0, solve for r, and you're done. Or you can do the whole procedure, which involves the part of the proof where you say assume y equals e to the rx. And when you plug that, so that means that y prime is r e to the rx, and y double prime is r squared e to the rx. So now, when you plug all of this in, you get r squared e to the rx plus 6r e to the rx plus 5e rx equals 0. And you see that you can factor out e rx, left you with r squared plus 6r plus 5 equal to 0. And since e to the x can never be 0 because it is asymptotic, right, to the x-axis, you can divide both sides by it, but when you divide 0 by it, it remains 0, and you get your characteristic equation.
So can we just literally leave it like as a squared plus 6r plus 5, or 6a plus 5? Right?
Yeah, so you go from there directly here.
So then we can just factor it here.
Oh, yeah. So all of this is I wanted to show you in one problem what's in the background, and this stays standard for all problems. So now you're going to factor this. You get r
plus 2.
I love this problem. Everyone's like, 2, 3, no, 5 and 1. What? We're going to take it outside now and figure out, or what? Want to take it outside? So which one is it? Plus 5 plus 1. Good. See, there's a civilized way to do this. From where R1 is negative 5, this is not Mortal Kombat, and then R2 is equal to negative 1. No. Exactly. So now I have the solution in terms of x to be c1 e to the negative 5x plus c2 e to the negative x. Ta-da! Why you're disappointed? That's it.
So then what's the difference between the homogeneous equation and the second order equations? What the second order equation right there?
Homogeneous has nothing to do with second or third order. That's not the order of the derivative. The homogeneous is equal to 0 or equal to a forcing term. When you have a forcing term there, we're going to learn the method of undetermined coefficients or variation of parameters that will take care of the non-homogeneous case. Now we're dealing only with the homogeneous case.
So, meaning it's just doing this.
Yes.
Oh, right.
So the second order deals with the fact that it was the second derivative was the one in charge.
Yes.
That's the second order. The word linear means that you don't have this situation happening, like y times this or something squared like that. And then homogeneous is just this part here, meaning it's equal to 0. If there is something else there, then we have to use, and you'll see that in the next few sections in this chapter.
Okay.
So that's this. Now, obviously, for those of you who are more interested in these kind of things, you are going to take the first and second derivative of this and plug those puppies here, here, and here, and check if this works. That's how it goes.
But you do have it. So then this term y, right? So you put that back in 5. Right? So we'll just take it to the back, or we put that back into the 6 one.
All right. So now, as you are factoring or looking for zeros in your polynomials, you have those three possible cases. There is the case where the where the zeros are real, repeated real, or complex, and we address those we address those now. Yes.
Is there a rule between, like, let's say you have the same exact exponents, let's say with -5 and -5?
That's what I'm trying to do now.
Oh, okay.
So patience, young Padawan. Exactly.
Never.
Yeah, you're going ahead of yourself. That's not physically possible.
What?
To go ahead of yourself. No.
It's so hard to wrap your head around to get it physically ahead.
It's impossible.
Wait, now we can wrap our head around ourselves?
Whoa. You're an owl.
You just took it to the next level. I was just going ahead. Now I need to wrap the head around it. It's just even worse. All right, that's fine. 3 cases, guys. So as we solve polynomial characteristic equation, solve characteristic equation, we can get, number 1, distinct real roots. Number 2, repeated real roots. 3, complex real root. Complex conjugate pairs. Kind of many. And now you are memorizing the solution string. So you actually are not solving these equations by integration or anything like that. You factor it, you recognize which type of answer you have, and you just use that form to write the answer. So for distinct roots, you will have R1, R2, R3, and whatever else. The solution is y of x or y of t is C1 e to the R1x plus C2 e to the R2x plus C3 e to the R3x plus ... whatever amount you have. Last one is obviously Rn, so plus Cn e to the Rn x. That's distinct roots. 2. Repeated roots, real roots. Now, there is the issue, because these roots produce produce solutions that are not linearly independent, i.e., they're dependent. So we have to fix them. So we have the repeated real roots, and that means that R1 is the same as R2, is the same as R3, is the same as R4, is equal to all of those. Well, I don't need R4, so I'm just going to cut it there. R3 equals to Rn of these roots. Right? So when you have the repeated roots, what you are going to do is you are going to pre-multiply this e to the, in this case, Rx, because they're all R, by x squared, x cubed, x to the 4th. So the solution is y of x is equal to, you have c1 e to the Rx, because all of these are actually R, plus c2x e to the Rx, plus c3x squared e to the Rx, plus dot, 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 plus cn x to the n e to the Rx. So you are multiplying. If you have a third degree, you will have only 1, 2, 3 terms. And then you will just have x and x squared. So just multiplying by this x, it makes it linearly independent. We must have linearly independent solutions for each one of these. Yes?
Wouldn't it be cn x to the n minus 1 is the Rx?
That's correct. Just plug it in, and your question is immediately answered. Plug it in. Van der Mode said that. Van der Mode with his matrix said that. But that's okay. I think it's mentioned in the book, but it might not be. You will look at page 128, and it's going to be clear as a day. Wait for the complex one. You're going to love it. Did the class prep? Oh, okay, good. That's why you're here. Complex conjugate pairs. Well, this is where your R1 is A plus BI, and the R2 is A minus BI. You have to have A equals A, B equals B, and then the sign in the middle is switched, which creates complex conjugate pair. And if that happens, you guys have the complex solutions, which produces the good old y of x is equal to e to the ax times cosine bx plus c1, hold on, c1 cosine bx, right, plus c2 sine bx. And let me just, can I? Yeah, I can. Give me 1 second, because I need to put this on a cloud. There we go. Now with this is on a cloud, we can keep talking. Yes?
This looking very suspicious to understand. Is there no I? Like, there's no I in front of time.
Oh yeah, you came to the complex thing. Yes, so you know that the cosine x is defined as e to the x plus, e to the ix, e to the negative ix over 2, right? So if you use the general form, right, like for distinct roots, you would have to write this right, times x. But when you separate this, you get e to the ax times e to the I bx. And then you can continue, right, until you get into the form. So that's where it comes from. So you will quickly catch up, because I know you like those proofs when I did those lectures. And that's the end. Now we just do examples, guys. The only thing that you must do for this is be able to factor your polynomials. If you're able to factor your polynomials, you will be able to recognize what type of a solution you have, and you must memorize the 3 cases, right? Or if it's repeated roots, you need to memorize that you have to multiply by x squared, x cubed of how many you have. So now let's take a look at some of the exercises. For instance, we have this. Let's go with 22. It looks awful, but we'll do it. 134. So 9y double prime plus 6y prime plus 4y is equal to 0. And we have y of 0 is equal to 3, and y prime of 0 is equal to 4. So this is problem 22. Why I put 9? All right. So I don't care how you factor this. You just have to factor it. All right. So whether it's factorable, you say, oh, I don't know how to factor any of this. Then use quadratic formula 100% of the time. If you don't know how to factor any of the methods, right, you would factor this as 9 times 4 is 36, and then try to find 2 numbers that, right, all that. But you know what? I'm just going to say the first, write characteristic equation, right? And once you do that, hit this with the quadratic formula if you don't want to bother with factoring. So you have negative b plus minus square root of b squared, right? Minus, ooh, shiny. Look at that, all over 18. So the answer over here is negative 1/3. It's a repeated root, because the plus minus square root that actually creates 2 solutions ended up being 0. So if you have a repeated root, that means that r is equal to r1 is equal to r2 is equal to negative 1/3. So you just write the solution because you memorized the form. It's c1 e to the negative 1/3 r plus, and since it's a repeated root, you have to multiply by x, so c2x e to the negative 1/3 x. It's not r, it's x. And this is general solution, right? This is general solution, but we have those initial conditions they want us to use to figure out C1 and C2. Now, initial conditions given to us are for function and for derivative, so I have to find the derivative here. And you know what? Derivative is not fun because the second part is the product rule, right? You have x times e to the x. So that's a product rule. Such is life. So we have negative 1/3 c1 e to the negative 1/3 x. No, because that's in the derivative.
Oh, yeah, okay.
Right? We have to keep it. Yeah. And now you have the product rule, so that will be a plus c2 times, keep the first, times derivative of the second, plus keep the second, times derivative of the first is just 1, so we don't have to worry about that. There we go. So now we have these two guys. Now, in the first one, use y of 0 is 3. Great. So now we have plug in 3 equals C1 plus 0, right? Do you see that? Because you have x is equal to, you all see that x is equal to 0 here, right? So when you plug that here, it kills the term. So we got that C1 is equal to 3. Nice. And now, from here, use y prime of 0 is equal to 4. And you calculate C2, exactly. So 4 is equal to negative 1/3. You know C1 is 3, so times 3. And then e to the 0 is 1, so don't have to do anything there. Plus C2 you don't know. But over here, this dies because x is equal to 0, so it's just times 1. So that's it. And you have negative 1 there, so C2 is 5. And now you write the particular solution, which is y of x is equal to, and then you have your C1, which is 3, e to the negative 1/3 x plus 5x e to the negative 1/3 x. And this is general solution. This is the end of the problem. Particular solution. Now, you're not always going to be lucky to have these guys work out so quickly. Sometimes you'll actually have to do 2 equations to unknown system, right, to find C1, C2. This was a nice case where we get to solve them quickly.
But if we're looking at the leader went to exam, you could put things that are nice and easy.
Exactly.
He gets it.
Do we have time for another one?
5 minutes?
Yes?
We have 5 minutes.
Oh, you have 5 minutes?
No, like 5. You can go now.
So?
If that's enough time, he said. Or is that enough time to go to the
Yeah, but you have nothing going on after this, so you're good.
There's a flash in.
They can wait outside. Exactly. Because I heard it's going to be raining tonight, so we might as well stay here.
I got another class.
Really? So let's quickly look at y third derivative plus 10y double derivative plus 25 y prime equals to 0. Y of 0 is 3. Y prime of 0 is 4. And y double prime of 0 is 3, 4, 5. Very creative. Very good. Bravo. All right, so characteristic equation from here would be immediately r cubed plus 10r squared plus 25r equal to 0. You see that you can kick r outside, which leaves you with r squared plus 10r plus 25 equal to 0. You might also quickly catch on that this is perfect, the square of binomial. So r and then r plus 5 squared equal to 0 because life. Or you can do the quadratic formula and just figure it out.
But you don't want to split that where it ends up being r plus 5.
Well, what you know is that the first one is r equals 0, and the second one is r equals negative 5 repeated. Right? Because it's a double.
Yeah.
That's why we learned about, in PreCalc 1, we learned about repeated roots and the multiplicity. If you remember the multiplicity M2, M3 from PreCalc 1, that's what it means. This is over here root M2, multiplicity 2, from PreCalc class. So now that you have these solutions, You just write out the solution. Your y of x is equal, it looks like g. Your y of x is equal to c1, and now you have e to the 0. Well, that's 1, right? You have e to the 0x because r is 0. So you e to the 0x, that's just e to the 0, but e to the 0 is 1, so we don't need it. So c1 plus c2 of e to the negative 5x, and then this one is repeated, so it gets x. So c3 x e to the negative 5x. So the first root is the distinct root. It gets its own term, but since it was 0, e to the 0 is 1, so it just constant survives. The second two are repeated from the -5, so you have to have the 1c2 and then the 1 with x. I was hoping to run into one that will have trig, but I guess your homework will be there. This is repeated root. So both of these are from the repeated root. But the first time you use -5 is not repeated. It's, you know, basic. The second one is repeated and it gets x. All right? And now we get to differentiate this 3 times, and we get to use the force, use the conditions to come up with c1, c2, c3. So the first derivative y prime is c1 dies. This gets to be -5 c2 e to the negative 5x, and then plus c3, and it's a product rule now. So copy the first time there, so -5x e to the negative 5x, plus copy the first derivative of the second, so it's just e to the negative 5x. And that's our first derivative. Then you have to do second derivative for the other solution. So y double prime is now the derivative over here is positive 25 c2 e to the negative 5x plus c3, and now the derivative in here, you have another product rule. It's going to be 25 x e negative 5x plus copy the second derivative of the first is -5, so it's -5 e negative 5x exactly, plus, and over here we have -5 e to the negative 5x. There we go. Perfect. No, because you have y and y prime and y double prime as initial conditions. That's all we need.
Oh, okay.
Right? So the first one, the first solution, this is problem 26. So from the first one, oh, by the way, I forgot to say this is general solution. We are going for particular now. So we use that y of 0 is 3, right? We have 3, 4, 5, yep. And when you plug everything in, we get 3 is equal to c1 plus c2 plus 0, because that one has an x is 0, so that kills that term. You see, you did not calculate c1 or c2. You actually have equation. You have to start that equation because you might come back to it. You will have to come back to it as a system of equations, or maybe you're going to calculate c1 or c2 later from some other equation, and then you go back and plug to find the other thing.
So you say C1 equals C2?
Oh yeah, you can put it in any order, but I'm just going to leave it there. So now y prime is 4 equals, and now I have -5 c2 e to the 0 is 1 plus c3, and then the first one dies, it's 0, so c3, that's it. So now you see that I have another equation which is just c2 and c3. So it looks like we'll have to solve 3 by 3 system of equations to deal with this. And last one is 5 equals 25 c2 times 1 plus c3 and this one dies. These two give you negative 10. So negative 10 C3, right? One more time, this one dies because of the 0 on x. These are the same, so negative 10 e to the 0, which is negative 10, good. All right. Now look, you can actually solve these two for C2, C3 first, and then when you have C2 from there, go back and calculate C1. So now I have these three equations. Solve for C1, C2, C3. Whatever witchcraft you can come up with to solve this, it is going to be good. So we have the bottom two equations times 5 on this equation. So that gives me 20 equals to negative 25 C2 plus 5 C3. Leave the bottom one the same, which is 25 C2 minus 10 C3. And now when you add equations, you get 25 is equal, these guys die, negative 5 C3, welcome C3 as negative 5. And then 4 equals negative 5 C2 minus 5. So negative 5 C2 is equal to 9. C2 equals negative 9 over 5. Awesome. And the last equation, C1 plus C2 equals C1 plus C2 equals to 3. Well, we know that the C1, we know C2 is negative 9/5. So negative 9 over 5 equals to 3. C1 is equal to 3 plus 9 over 5, which is 15 plus 9 over 5 on a common denominator, 24 over 5. And there's the C1. And now you plug everything in, yes. So y of x is equal to C1, which is 24 over 5, plus C2, so it's minus 9 over 5, I forgot it, negative 5x. Oh yes, you just, I almost got a heart attack that I did something wrong over here. Yeah, just don't talk to me to the SS class. And then C3 is negative 5 x e to the negative 5x. Oh, I so need that ta-da button. Ta-da! This is particular solution. Awesome, right? I guess these guys want to have their algebra in peace, so we'll continue this fun next Tuesday. So guys, I will see you on Tuesday.